All right, good afternoon, survey students. We are going to have our class online today. You've already seen part of it, and I just want to finish it off by answering your questions that we have specifically about A World from Dust. The section that we have to read is chapters 4 through 6, and so I've got your questions and comments, and I put them in a rough order. We're going to move from the sort of abstract to the concrete as we do this, but we're always going to have lots of connections to what we talked about in lab, and so in lab and in lecture. So we're going to have basically look for those connections. If you ask a question about it and I'm thinking about it, it very well might be in my mind as I'm writing the test, and I'll try to let me know if you have any more questions about the test. But it's going to be choose what you want, and it's going to be open book. And I've seen some evidence that you all are looking at the book. That's good. Be familiar with the book and think about these things as we go through. So the first thing I want to do is I do want to clarify one point I had on the last slide where I got myself confused, because I said, how many degrees of freedom do we have in this rather complicated system? You have a liquid phase that's mixed, and you have solid B, and then you have the potential to make solid C and solid A. When you start, you just have solid B. And so what you have is you have the equation that is 3 minus 2 plus 2 equals 3. And that sort of confused me a little bit because we have a two-dimensional graph below, and we have that's representing 2 degrees of freedom. But the thing that doesn't represent is that there's an extra degree of freedom. So why are we saying there's 3 degrees of freedom? How are we fitting that with a 2 degree of freedom graph on the bottom there? The way we're doing it is we have temperature as the 3rd degree of freedom. In a sense, there's a temperature axis that sort of runs perpendicular to everything else. We're not really showing that. We don't really need to, because what we want to talk about is if we just change the temperature and the system changes as a result, how is the system going to change? As we cool it down, the one thing we know is cooling down the temperature will produce more solid. And so that's going to move us down. It's going to make there be more B in solid and less B in solution. That means we're going to be moving away from the B axis. And we're going to be moving away until we hit a line. Then we'll be moving on that line until we hit the point. And then we'll stay at that point, because at the point, we actually have 0 degrees of freedom there. Technically, we have the temperature is the fixed degree of freedom that we come to there. So the reason is because temperature is a degree of freedom, F actually equals 3, but then we reserve 1 for the temperature. F equals 2, therefore a two-dimensional plot will explain things well. The B will move down to be on the line. We lose a degree of freedom. It becomes a 1, F equals 1, which remember that is represented as a line on this graph. And again, the temperature can change, but we are going to, if we're not doing anything else to the system, changing the temperature will cause it to stay on that line. It's going to stay on the line where you have both phases present. Once the phase appears, then basically you have lost a degree of freedom that before you had, because you had a degree of freedom to move around in the two-dimensional area. This is kind of weird, but I think it's cool that just by cooling this system down, you can reach a point where you know what the eutectic point, which is a particular mole fraction of A, B, and C in solution, and then you have all 3 phases. It's like the triple point, but it's with a solution rather than with a pure substance and temperature pressure graph. Okay, a solution and mole fraction graph. If you can get this is the most advanced problem for mole fraction type thinking. If you can get this, you're good for the test. I want you to have that image of when your degrees of freedom go down, you stay on the line because you don't have freedom to move off the line anymore. Once you have the degree of freedom gone down, you're stuck. Okay? So, all that is talking about how you can balance things, and it's the importance of not forgetting things, like not forgetting that temperature is a degree of freedom. And so we have our first question that was about actually energy balances and imbalances on Earth. And I love this question because this is exactly what Lord Kelvin was thinking, in a sense, and I'll explain in a second. But it's thinking about these balances, and you want to be sure that you're thinking about them the right way and you're not missing anything. So if the heat, the idea is, if we have heat being produced on the Earth, isn't it going to be constantly heating up? If we have a constant flow towards second law, if we have heat is easier than work, and we're always producing a little bit of heat, right? Then eventually won't heat win? And the basic answer is yes, this is why we have the cosmological concept of the heat death of the universe. If the second law is all there is, then basically everything's going to spread out until it can't spread out anymore. And this will happen on a small scale on the Earth. And so there would be a heat a heat buildup if we don't have anything else going on. The good news is there's a few other things going on, and you want to make sure that you're accounting for all the processes as you're thinking about how these things work. The second law applies to the entire universe. If you have a system within that universe, it can pass entropy in and out. Within the system, you have irreversible increasing entropy. But if you have reversible changes in the system, that entropy can actually move in and out of the system. And so that's that main figure that we have on the front page of the book. Notice that it's not just about DIS, it's also about DES, which has to do with the reversible rather than irreversible changes internal to the system, and the transfer of heat across even a closed system's boundary. Okay. But this is a tough thing to think about. It's kind of a theme of the whole class. And I want to say that thinking about the Earth as a planet, just got to remember that there are surprises on a planetary scale. Planets are big. And you've got to think about all the possibilities. For example, Lord Kelvin once calculated that the Earth must be, I think he said less than 1 million years old. I forget what the number was, but it was definitely a lot less. It looks like it's a 4.7 billion years old from the rocks. And they knew even in Lord Kelvin's time that it looked to be billions of years old. And Lord Kelvin did some calculations, and he came out with, well, if you just assume thermodynamics, the planet forms from molten earth and iron and things like that. And we know how iron holds heat. So we can calculate how it would lose the heat to space and cool off over time. And he calculated that even with, I believe he included the crust being able to form and the crust being able to hold on the heat a little bit more, because they knew about that at the time. And then he calculated how old the Earth is based on how hot it is now and how much it could have cooled. And he calculated that it was like 1 million years rather than 1 billion years. Again, I don't know the exact numbers, but I definitely know the story is right. And according to the thermodynamics that we presented to you in class, he's completely right. He actually did everything right. He just missed one thing, which was that there was a kind of energy movement, a kind of atomic decay that would produce heat that he didn't have any idea about, because nobody knew about radioactivity, the structure of the nucleus, nuclear chemistry, where you have a nucleus decaying. When the nucleus decays, that releases heat. It turns out that once you know all those things and you calculate how much radioactivity heats up the Earth, it actually ends up being perfectly consistent with the geological evidence that it's billions of years old rather than millions. This is a great story because it shows how you just don't always have all the information. So it's important to make sure you've accounted for everything. There was an energy input into the system from nuclear energy that was not known at all, because they didn't even know about the nucleus until after Lord Rutherford, who came after Lord Kelvin. Again, I need to look this up to be completely sure, but I'm sure about the basic point that Lord Kelvin made his mistake, but I don't really hold him accountable for that. So energy flows are actually a big part of this class, and the important thing to think about them is that, yeah, you can calculate some things at equilibrium, but you've got to account for the flow of energy as well. The basic thing that runs the whole Earth is that the sun has high energy, low entropy protons. They're very held together. They're very tightly wavelengthed. That's one thing to talk about them. Then they hit the Earth and they leave. The sun is at 6,000 K, and it actually generates light. One of the topics at the end of class is going to be how that light changes as it travels to the Earth. And the answer is it doesn't lose energy, really. There's nothing to lose energy to. So it basically reaches the Earth with the 6,000 K entropy of the sun, the energy from the sun, I should say. And then it gets spread out by the Earth. The wavelengths get stretched out. The Earth will release many lower energy photons. And it's that difference that makes the Earth an open system, exactly like the questioner said. An open system that allows us to do something with the difference between the high energy photons coming in and the low energy photons coming out. We can do work as a result. And you can calculate exactly how much energy comes in. I want to remind you of this particular figure. I believe you saw this in Chapter 2. In Chapter 3, he actually returns it, but he doesn't give us the answer. And so because we don't have the answer to it, I assigned it to 3422. But he says, go back to this figure that you've seen before of all the energies going in and convert them to entropies. Well, that's actually not very hard, because what you can do, we're talking about radiant energy here, but all you need is to take this kilojoules per year and convert it by dividing it by the proper temperature at each time. And again, with these problems, you can look it up if you need to. So I didn't assign this problem to you, but you did see this energy flow before. And just notice in this, most of the energy gets reflected. And most of the energy from the sun actually never gets caught by the Earth at all. In fact, this is one mistake that I made. I was thinking about, and it's possible that there's a mistake about this in the book, because I was always thinking about things as being sort of Earth-centric, and then I was like, well, if the Earth is increasing entropy, but it's so small relative to the energy from the sun, and the Earth only takes up this little sphere of the energy coming out from the sun, how can we really say it's significant that the Earth is increasing entropy? And that's true on an absolute scale. The Earth is not increasing the entropy from the sun by even even a significant amount. It's hard to even measure on that scale. But the whole point is, it's not about the absolute amount of energy, entropy that the sun's giving out. It's about the amount of entropy that the Earth is receiving and the flow of that entropy through. And so because this was a problem that was assigned to the other group, I just want to remind you of this, and so only a small fraction of that energy is actually absorbed by photosynthesis, and that powers the rest of life that goes on. We can also talk about how much human energy use is relative to the amount absorbed by photosynthesis. And of course, humans can get things out of underneath the surface and things like that, geothermal energy. This is a really cool concept right here. But I just want to remind you, you got to account for all the energy, and you got to account for it in terms of a flow for the system that you're interested in, rather than an overall amount. And on that scale, the Earth would be a cold rock if it wasn't for compensating processes and the fact that there are flows on its surface rather than we're talking about an absolute amount of entropy from the sun, things like that. So all this is completely right. Earth is an open system, gets energy from the sun, sends energy back to space. You can talk about that in terms of wavelength of radiant light, or you can talk about it in terms of entropy. It just depends on what units you're using, really. And so the idea is, as we do all this work, the planet is sort of naturally heating up from it. But the thing is, the scale of this heating up is probably not that large. At least it's manageable, and it might be manageable by controlling some of the other energy flows. You might have heard, actually it was announced today, that people are going to try geoengineering by changing the reflectivity of the clouds. The reason why that could be good is because it could change that other flow that we have on the other part of the figure to help us with the fact that human energy use is producing spread out heat. All the work that we're doing is producing heat on its own that wouldn't be there. So yeah, keep thinking in these terms. Just make sure that you expand your thinking to include not just S, but ds dt and dis dt. And remember that dISdt moves to 0 over time. If you have a flow that will set up, it will stabilize not just a configuration, but a system of dynamic movement. This is Prigogine's whole thing. And his whole thing is that actually entropy, second law, if the flow is moving in the right direction, the flow can set up order. And then you can actually have entropy powering order. And so in terms of heat doesn't just have to accumulate. You can send it somewhere. You can change the system so that other inputs go down rather than if you're worried about the output of the system, you can change the input. That's what they're doing with changing cloud reflectivity. By the way, I'm not sure that's a great idea, but I'm just mentioning it as an example. And so this is what Prigogine's whole thing is. And in fact, I want to bring it back to this. There was a prediction, there's a Landau theory that made a prediction of what would happen near the critical point. So like you see, you have the critical point right here, and we're talking about the critical point is point C, C for critical. But as you're moving along the liquid-gas line, you define the critical point by the point at which the phase difference between liquid and gas disappears. You can no longer see the line between them. And when you're moving from A to B, you still see it. At C, you see it disappear. And when you're at point D, you no longer see it. That's the observation of the critical point, understanding why it happens and what happens near it in terms of free energy is the object of research. And so they were doing, one of the ways to look at the critical point is to make a graph of G versus molar volume, G versus V. And you see that you have 4 different graphs of the 4 different points right here. There was Landau theory, but it gave predictions of what would go on. It gave these predictions. They tried to match it up to experiment, and it didn't work, especially for point D, I believe. Once you got off the line, you couldn't predict what the supercritical fluid was actually going to be doing. And Prigogine makes the argument that he this is giving chaotic behavior because they weren't accounting for long-range fluctuations correctly. Long-range fluctuations have to do with flows, with time, with dISdt rather than just plain S. So I just want to point out that this is what Prigogine gets us, and this is one of the reasons why he can say, hey, I was right, because we can actually understand this behavior better. The problem is when you have a flat free energy surface, telling where on that surface you're going to start the behavior from, where you're going to be on that surface once you're past the point. The flat energy surface, the normal theory does not allow you to predict what will happen. Prigogine's work allows you to say there can be long-range fluctuations that influence what will happen when you get to point D. Basically, for point D, you see at point A you have 2 minima, 2 places to be. At point C, you have a flat G, and so you don't know where you're going to be. Past point C, you're going to be at a specific point again when you have G versus molar volume. And predicting where that point is going to be, Prigogine says there's certain things about it you can't predict. But then if you account for the way things flow and long-range fluctuations, then you can actually at least understand why you can't predict this thing. Okay. I just wanted to mention that because it actually does connect with what does Prigogine teach us that other people don't. So I want to connect this with another questioner's comment that was about how flows can explain things better than equilibrium. First, there was an additional question, so I'll answer this one. This is about making amino acids and the idea that the Earth could make its own amino acids. If the Earth could make its own amino acids instead of ordering out, then why would there need to be some biomolecules on an asteroid in the first place? And the answer is, if it could to a certain extent, maybe there wouldn't need to be. And we don't really know, but maybe there would need to be if the Earth couldn't make particular kinds of amino acids, and instead those amino acids came down, maybe the sulfur-containing ones came down from asteroids, and that helped with the whole system. It's a complicated system, but you don't know, and so you think about all the places amino acids could come from until you have some evidence that they came from one place and not another. Right now, it's not that there's too few places for amino acids to come from. In a sense, there's too many. because there's these different possibilities, but then you can talk about, well, how possible are they really? But that's why you have a book and more research to do after reading the book. So chapter 5 talks about this, and this is basically, this comment is just thinking through the fact that larger amino acids are more ordered. In a sense, there's more of an entropy reduction when you form those bonds. The good news is, when you form the bonds, that actually has an enthalpy component, in a sense, that allows those to stay in place. But yes, there is a configurational entropy loss that is greater for making something like a big amino acid like tryptophan. And so the question is, are large amino acids like just too hard to make? Because I'll acknowledge that they're hard. But this is thinking through, well, if you actually gain enough entropy elsewhere, it just means that you need to gain more entropy elsewhere. And if you have a flow, notice that this is a seafloor thermal vent is proposed to make amino acids this way. And if you have a constant flow, again, you have the flow that could provide some order and could allow you not to defy the second law of thermodynamics, but to point it in a particular direction. The flow, which is an entropy-rich sort of configuration, is actually, if it produces a chemical reaction and then carries the amino acids away to where they can be stable away from the heat, well, that right there is the entropy of the flow helping you to pay the price for the entropy of bringing those atoms together in the amino acid. And like it says down here, it's not a deal breaker from a physical chemistry standpoint. Yeah, and this is a little bit like Lord Kelvin's argument. There's things that we don't know and we don't add it into the equation, but there are things along these lines that we have figured out. So here's the question. It's actually also related to origin of life. And so considering what are we arguing here? Are we arguing that life does exist and something made those molecules, or is it arguing that the dumb chemistry was able to take place in those bubbles, which given enough time would lead to something alive? Basically, is life built up, or is it coded into the situation? And honestly, this is the basic philosophical question that goes back to at least one reading of the difference between Plato and Aristotle, although both of them were on the same page when it came to this. They said life comes from life. But the question of how that happens is a really interesting question to ask. And so there's very fascinating things. This is a very old question. And how could dead chemistry make life? And the one issue so this is a very personal answer that you take to all of these. There are many ways to answer this. But I don't want to say that the life that emerges is an illusion or something laid on top of dead matter. Instead, I want to reverse it. And I want to say that matter is not dead, but in a sense, matter is alive because it contributes to life. And we've seen this movement throughout the universe where we end up coming up with life and then mind. And in fact, of course, this whole book is about the transition to life. And I don't think there's one part of it, the DNA code, translation, transcription. I think that might be the thing that you cannot explain. Everything else, I suspect that you might be able to explain most other parts of it. But the code, maybe you can't explain it. And then on the other end of things, I think the more difficult transition is the transition to mind. This is also a big argument. Aren't the little minds that we see around us that evolved into the big mind, doesn't that show that the transition to mind isn't a sharp transition? I actually don't think so. I think that I want to prioritize mind, and again, this is from the philosophers that I've read, including Plato and Aristotle, and also Christians like Gregory of Nyssa, and the church, the Eastern Church Orthodox in the 4th century A.D. with the creeds and all that stuff. Okay, so this is a huge question, but I just want to say mind is actually the more difficult thing to me than life. And because it's difficult, I think there is no way to bridge between mind and matter. And therefore, I'm not going to say that mind comes first, is what I am going to say. I'm not going to say that matter comes first. So mind is able to, and there was some way in which mind was able to take advantage of a long evolutionary process that eventually resulted in us. But that's not because the mind is an illusion on a universe of death, but that the idea that matter, even matter, is not dead. That's a universe of life and mind rather than a universe of death and mindlessness. You didn't know you were signing up for this, and you were signing up for a PChem class. And this is not going to be on the test, but it's on the test of life. What you think about these things. And I just want to say, the transition to consciousness is what I really want to think about. And I do want to prioritize mind and our recognition. When you recognize physical chemistry going on, you are actually participating in the life of the mind. And you are participating in the life and order of the universe, which I believe comes from the ultimate mind itself, that we all participate in. So, but that's philosophy, and that's actually theology. So the cool thing about Prigogine is most people think of the second law of thermodynamics as being a law of death. And in some ways it is. Death and life do coexist, and they matter. But ultimately, Prigogine says that even the second law can be an engine of life and can cause things to happen. So even the second law, in a sense, is alive if you look at it the right way. And in fact, this does go back to the first question, because it was kind of like, how can this, given the second law, how can the earth still be alive? You know, and are we worried about the earth dying? And yeah, we need to steward it. But there's some things that I believe that we can have the hope that we are placed in an alive universe. And our job is to participate with it and to look out for the others that are also participating in it. Anyways, okay. And now we get to the chapter 6 question, which is, how is a WInogradsky column like that 4-layer system? I want to use that as a model. Remember, I showed you that 4-layer system. You mix it up, and it still separates out into 4 different phases. And so we're talking about all of chapter 7 in modern thermodynamics is about phase changes. And I honestly had never really put it together as clearly as this question made me put it together. So thank you for this question. This is a great question. The WInogradsky column orders in the same way that the 4-layer liquid system orders. In fact, I could even put it in a tube, and we could have the same tube, and it would have little colored layers that look a lot like the 4 layers. It would separate out. It would take more time, but it would eventually separate out. So how are the layers that form in the WInogradsky column like phase differences? And this is just a fantastic question, because I don't know. But I suspect that there's something there if you look at it the right way. So here's my way of thinking it through. So the 4-layer liquid system has 2 sorts of energy sort of interacting. There's the chemical potentials, the little mu's, that reflect that the like bonds like much better than it binds the other. And the really cool thing about the 4-layer system is you have 4 systems where like binds like better than it binds any of the 3 others. That's unusual. It took some work to find that. But that's what creates each phase. And you can think about that in terms of mu, delta G, bonding between the phases versus bonding with the other 3. When the bonds form between the phases, because like associates with like, then you end up with a whole series that you can see where it's all like. And that's not even the end of it, because they need to have different densities. They would actually all stay mixed if they all had the same density. But because we're in gravity, or if we were in 0G, they would all stay mixed. But because we have gravity pulling it down, the high density phases will be pulled down, the low density will be pulled up, or pushed up, or excluded. And so this is fascinatingly like it looks alive. Remember, that's one of the reasons why I showed it to you. And this is another one of my things. This looks alive. It's not an illusion. In a small and limited sense, it is participating in life's processes, even though it's not alive itself. Okay? And we're recognizing it as life. So while it's unmixing, you even see little things that look like cell-like spherical structures that the second questioner asked about. So in the WInogradsky column, the redox potential replaces gravity. That's the thing that's pulling the layers up or down. How are they linked together? They're linked together by metabolisms, by cycles of atoms rather than bonds between atoms. But each chemotype maybe could be represented by a single overall metabolic reaction, the same way we can represent an entire molecule with a single chemical potential. I don't know, but would that allow them to associate? Would that pull them together? And then we'd have the separation from up to down that would be caused by oxygen at the top and no oxygen at the bottom. That would be redox potential separation, which, by the way, is a future chapter that we'll talk about. So the metabolites shared by the microbes, are they replacing the chemical potentials? Is it the way the cycles fit together? Because those really are circles of reactions rather than a arrow of a reaction, and yet we can talk about them with something like chemical potential. It seems like someone smarter than me is going to have to put that together. Maybe it's you. Who knows? So how many different things can we think of phase transitions? This is fascinating because I literally saw this by chance on my social media feed today. There are other people that are looking at other steps in evolution as phase transitions. And here's something, and the question is, how do you measure whether you're a eukaryote or a prokaryote, which phase of evolution you're in? How do you measure that with a quantitative number? What they chose to do is they used protein length versus gene length, because they noted that there was actually a straight line that you could do, and that line has an inflection in it. I'm not going to go into this entirely, but it's fascinatingly relevant that we can think of this transition, this chapter 7 transition, as a phase transition. So why not think about the association of microbial communities, which is chapter 6 topic, as also a phase transition? So I will let you think about that and chew on that. Thanks for giving me lots to talk about. This is a bit longer than I thought about and a bit more philosophical, but I hope you see how this connects to the class and you're making these connections, which is my whole point. So thank you for your time. See you for the test on Friday at 4 p.m.